They got like 15 million hits.
She got famous, but not the way she was.
Oh, like kind of like that guy that was terrible. Like the guy from American Idol that was so bad, and everybody felt bad for him, and he had this concert. And
Yeah. He got the record deal out of it.
That guy's awesome. He loved it. He was awesome.
He was awesome. He was a loser.
Therefore, it worked.
Okay, so the comparison test. Off we go. Let's see. So let's set it up. So the comparison test for series, as you would imagine, is very, very, very similar to the comparison test for improper integrals. So, let a sub n and b sub n be positive sequences such that a sub n is less than or equal to b sub n, and they're both greater than 0. I guess that's redundant, but oh well. Then if so, just like, all right, so I'm going to do part of it, and you guys are going to help me fill in the gaps. If blah converges, then blah converges. And if blah diverges, then blah blah diverges.
It would be interchangeable for you to
Okay. So, what's the correct order? If b sub n converges, then a sub n converges. Why is that? Because b is the larger sequence, right? So if the larger one converges, then the smaller one has to converge. And so then if the
smaller one diverges, the larger one also has to.
So if a sub n diverges, then b sub n also diverges. Okay, so let's do a partial proof. Let's do just the first one. This one is even easier than the other one we did. So let's write out. So suppose the series b sub n converges. Okay, so hint: we're using monotonic sequence theorem. Okay, so what do we do? What do we want to show that converges? The always series converges if the series converges if the
limit exists.
no if the partial sums converge, right? Partial sums. Okay, so oh, hurts. Okay, so so the partial sums. So let's write this down. So so I want to show that the partial sum of the a's, right? So this is what I want to show converges. Okay, so what do I know about that? If I want to use the monotonic sequence theorem, yes, it is. So what are our assumptions we have? So these are the assumptions that we have to use. We know that the sequence are positive. We have this inequality, And we know in this case that B sub n, the series B sub n converges. So the partial sums with A are
They must converge.
they're less than what? This partial sum is less than or equal to
Partial sum of B and
yeah. Okay, so the partial sums of B sub n's, but then what do I know about the series of B sub n? What do I know about that? Yep. Since this converges, then S sub n is it is, come on guys, it's right there. So this converges, right? The series converges. So, and since the sum of all the A's is less than the B's, then that means that it is
monotonic.
no, the other one. Yes, it's bounded, right? Right? It's bounded because look, it's bounded. See, look, you have this, so the sum of A's is bounded by the sum of B's, right? But the sum of B's converges to some number, right? So that means that it's bounded by whatever the B's converge to. Okay, so S sub n is bounded, and so it's bounded, and then S sub n is monotonic because? Why is it monotonic? Monotonically increasing. Why? It's because of another one of the assumptions. Which one of the assumptions implies that it's monotonic? Yeah. Because the sequence is positive, right? My pen is not working properly. It's giving me trouble. Okay. All right. So, and then 2 is proved similarly, just in the other direction. Okay. So let's do some examples. So let's say we want to use the comparison test for the sum of n cubed over n to the 4th minus 1. So n cubed over n to the 4th minus 1. Okay, so I want to use the comparison test. So it's very similar to the comparison test with improper integrals. I look at this and then I want to compare it to something that's similar but that's easy to, that I already know whether it converges or not. And typically it's using the P series. So what do you want to compare it to? So what are you thinking? So in your head you're thinking compare to whether it converges or diverges using the comparison test. So remember, the idea is to kind of remove the fluff, the extra things, the terms that don't really affect the series much once you go out to n goes to infinity. Yeah, that -1 is kind of in the way. So if you imagine getting rid of that -1, what does it turn into?
1 over n.
Yeah, n cubed over n to the 4th. And so that turns into 1 over n, right? So this is what you want to compare it to. Now, before you can compare it to that, though, you need to have the correct inequality, right? So we can start off with n to the 4th minus 1. And n to the fourth. So what's our inequality look like there? If I compare these two, n to the fourth minus 1 is less than n to the fourth, right? Okay, so this implies that 1 over n to the fourth minus 1 is greater than 1 over n to the fourth, right? And since n is greater than 1, well, greater than or equal to 1, then you can just put an n cubed on top of both of these, right? And keep the same inequality. Do you guys agree? Right? So they're both, all of these are positive, right? So you multiply both sides by n cubed, so that doesn't change the inequality, right? Okay, but now this one on the right, this is equal to 1 over n, right? Okay, so then the issue is, so we have that, we have the inequality that we think we want, right? And the problem always with the comparison test is you're not always sure you're going to get the one that the direction of the inequality that you want, right? So we'll talk about how to deal with that later. But so what do I know? So we have that inequality, and since the series is a divergent p-series, then, so is that what I want? Does that imply that this one also diverges?
Yeah. No. Less than diverges. Yeah. Less.
It does, right? So the smaller one diverges, so that means that the greater one also diverges. So that means that the series n cubed over n to the fourth minus 1 also diverges by the
Comparison test.
yeah. Also diverges by comparison test. Okay. So notice though that before we do another example, just so the comparison test is very useful, but sometimes it can be annoyingly in what's the right word? No, just annoyingly difficult to implement. For example, notice that if I change this to n to the fourth plus 1, my inequality, they all shift, right? So this would turn into greater than. So if this is plus, then this would turn into less than, right? So notice what ends up happening is that tiny change makes all of my inequalities go the other way, right? And so with this inequality, even though the series really is almost identical in terms of convergence, but because of this, my inequalities are backwards, right? Because here I have that the larger one diverges, so that does not necessarily mean that the smaller one also diverges. So that can be one of the definite challenges to dealing with the comparison test, but we'll have a solution for that soon. What is it? Did you have a question? Yeah.
Kind of like to do with the improper integrals with the.
No, it'll be actually simpler than that. Okay, all right. Let's do another one. Another example. Let's see. How about cosine of n over n squared plus 1? So we want to use the comparison test to determine whether cosine squared over n squared plus 1 converges or diverges. Okay, so what do we do? So a good thing to do is take a look at it and decide, like think about whether it looks like it's going to converge or not. What do you think? What does your gut tell you?
It's gonna diverge.
Why do you say that it's going to diverge? What leads you to believe?
Because
It's going to converge. The top part, the numerator is going to fluctuate. It's going to fluctuate between between 0 and 1.
Okay.
And the denominator is going to be increasing.
Yes. So the numerator is near 0 and 1, right? Oscillating between 0 and 1. The denominator is n squared plus 1. So your gut tells you that it's going to converge because what's the one piece that tells you, oh, this is probably going to converge?
The larger number on the bottom is going to increase larger than the top number faster.
But remember, just because the sequence goes to 0 doesn't mean it's going to converge. What about it tells you that I'm pretty sure this converges? I mean, you're right, it does converge, but what tells you?
the exponent. No.
Yes.
The
Okay.
exponent would cause it to converge.
But what about the exponent? It's squared, right? And what are we? Yeah, exactly. So you think of the p series, and you go, okay. So the p series in the denominator you have n squared. That's going to converge. The top isn't really affecting it that much. It just goes between 0 and 1. So this is probably going to converge, right? So it's good to have an idea of what is happening before you, proceed. Okay. All right. So we imagine that it converges, and so we want to compare to 1 over n squared, right? That's what we're thinking of, which converges.
We want a smaller something to compare it with.
We want this one to be less than 1 over n squared, right? So the greater one converges, so then the smaller one also converges, right? Okay, so as usual, when we're dealing with trig functions, what do we know about cosine squared? Yeah. So cosine is between negative 1 and 1. So cosine squared is between 0 and 1. Okay. So this means that cosine squared n over n squared plus 1 is less than or equal to 1 over n squared plus 1, right? You guys agree? And can I do another inequality there where it's less than? Is this one 1 over n squared plus 1 less than 1 over n squared? It is, right? Does that make sense? Because the denominator is 1 bigger, so it's going to be less. And this is the inequality I was looking for, right? I want it to be less than the convergent one. So then I can just say, since the series 1 over n squared is a convergent p-series, then cosine squared n over n squared plus 1 converges by the comparison test. Okay. Does that make sense? Comparison test? Thumbs up? Go. All systems go. Okay. But again, simple little things like changing this to a negative would throw this into the more work category, right? Try to figure out how to deal with that tiny change. So for that, what we can do, we have a new theorem, brand new theorem, and actually there's a similar one for improper integrals, but we didn't do it. Maybe I'll give it to you later for fun. But it's called the limit comparison test. The limit comparison test. My pen is having problems today. Okay. So let A sub n and B sub n be, again, positive sequences such that the limit as n goes to infinity of the ratio of A sub n and B sub n is equal to some number L. Well, no, I'll put this down here better. Okay. So if L is some positive number, then either both, well, let me just say, okay, no.
Can it be negative? They're both positive?
No. Yeah, so the negative numbers are completely excluded because they're both positive. Yeah. But I want to distinguish between L greater than 0 and L equal to 0. Yeah. So then both series, both A sub n and B sub n, either they both converge or both diverge. If L is equal to 0 and the series B sub n converges, then the infinite series of A sub n also converges. Okay. All right. Proof. I'll give you a hint. It involves the no. The same one we've been. What is it? No, the one we've been using. No. Okay. I guess we will see. Okay, so let's see. Let's prove. Let's do. So we'll do a part of it again. So let's assume the series of B sub n converges, and L is greater than or equal to 0. Okay, so we have the series B sub n converges. This proof is a little bit more involved than the other ones, but not too bad. I'll help you guys get started. So L is some number, right? Okay, so since L is some number, then there exists, we've used this idea before actually. There exists some number, let's call it m, greater than 0, such that m is in between 0 and L. Yes? Oh, no, the other way around, sorry. L is in between 0 and M. That would have not worked. Okay. All right. So this is using the definition of a limit. So since the limit as n goes to infinity of a sub n over b sub n is equal to L. So what does that mean intuitively? Or if you think about the definition, that means that what? Yes, it converges to L, but what does that mean? If you're looking at this sequence, a sub n over b sub n and L, what is happening? Convergence means, remember we talked about this? We said intuitively it means that
It's going somewhere.
it's yes.
Does that mean they each convert individually?
It
No.
means that B sub n is going somewhere faster than A sub n.
No. So don't forget about the ratio. Pretend this is just a sequence. Just the remember the definition. You had that the
They're
distance.
bounded within epsilon. There's epsilon.
Yes. So, but what does that mean?
Bounded
That
down.
the absolute value of the sequence and the limit. What does that mean? Absolute value means intuitively.
Oh, it's always positive.
What does the absolute value mean? Absolute value of a difference?
Some value.
It's the distance, right? The distance from each other? No? No, not.
Oh, it's
Okay.
Right? So so remember we said that what the definition of a limit tells us, the absolute value of a sub n minus L less than epsilon, that means that if that limit exists, if it converges, that means that we can eventually get the terms of the sequence to be as close as we want to L, right? That's what that means? No? You guys forgot that. We talked about it. So, what is it? No. You don't remember that. So remember that, no? Okay. All right, well, so there's your refresher then. So this means that as n goes to infinity, it's kind of late for this deep of a conversation, I know. But
Thank God someone figured it out.
so as n goes to infinity, this sequence a sub n over b sub n, we can get it as close to L as we want, right? So if you want it to be 0.1 away, you can. If you want it to be 0.00001 away, you can. If you want it to be whatever distance away from it, you can. Yes?
Like,
Yeah.
I think
Okay.
it's something like that.
What is it? So what that means, so that's what we're, so you have to know that to be able, so that this makes sense. So what this means, so since the limit as n goes to infinity of a sub n over b sub n is equal to L, there exists, I won't say some number, but, so n greater than 0, such that such that 0, so a sub n over b sub n is in between 0 and m for all n greater than that number. So that's what we mean by as close as we want. So basically you have L, which is in between 0 and m, right? And since A sub n over B sub n converge to L, that means that if we go far enough into the sequence, we can get it so that all those terms after we're saying this capital N are also in between 0 and m. Does that make sense? So imagine this sequence, A sub n over B sub n, being really, really close to L. So if it's really, really close to L, then it's in between right there, right? Does that make sense? Okay. So now what? Now what can we say? Do you guys remember what we were doing? Okay. We want to show let's remember. So critical mass is being reached, I know. But okay, we have that series converges, right? B sub n, series B sub n converges. We're trying to show that the series of A sub n also converges, yes? Okay, so okay. So then okay, so from that inequality, A sub n is less than or equal to what?
M times B sub n.
M times B sub n, right? Yes? Okay. And since the series B sub n, what does that do? That converges, right? So since that converges, then what's true about the series of M times B sub n? Also converges, yes, that is correct. Also converges. So what does that tell you about the exactly. The infinite series of A sub n also converges from the
comparison.
Yep. Converges by the comparison test, right? Converges by the comparison test. Good times?
Sure.
Yeah, we did it. Okay, all right. Okay, so the reason why this is, so I think maybe we forgot why we even bothered writing down this this theorem. The reason why this is going to help us is we basically are going to use it for those times when we want to use the comparison test, but the inequalities don't work out very nicely. We can use the limit comparison test and get very similar results. So like if we go back, for example, to the one that we did right here. So let's do this one, the modified one, the one that we decided that would be an annoyance with the comparison test. So it was, wait, let me see. So so this is the example that we did earlier. The series 1 to infinity of n cubed over n to the fourth. We did minus 1, right? But if we change it to plus 1, then we don't get the inequalities we want. Then we would, if we wanted to do the comparison test, we would have to do some more, funny things. But we're going to apply the limit comparison test, LCT for short, with the same sequence. So we are still going to compare with 1 over n. So you look at it the same way. Right, you go, okay, well this kind of looks like n cubed over n to the fourth, which is 1 over n. And so So you look at it and you go, okay, so you take the limit as n goes to infinity of a sub n over b sub n. So you take the ratio of the two. So n cubed over n to the fourth plus 1 over 1 over n. And you just take this limit. So you go, okay, this is equal to the limit as n goes to infinity of what? Do some algebra there.
Yeah.
N to the fourth over n to the fourth plus 1, right? And what's that equal to? 1, right? So 1, that's greater than 0, right? Okay, greater than 0. So since that series diverges, then the series n cubed over n to the fourth plus 1 also diverges. Does that make sense? So useful, right? So, any questions?
Can you do another example?
Yeah, sure. Yeah. See, that was so easy that you guys are flummoxed. Flummoxed. I don't even know what that means, but I wanted to say it. Let's see.
Bamboozled.
How about square root of n over n minus 1? So square root of n over n minus 1. Okay. So let's say I want to use the limit comparison test with, what would I compare it to?
Reduce down to 1 over, or n is
Oh, wait.
1/2.
Can't start at 1 because you have to start at 2. Because the denominator is 0 at 1. So what would we compare it to? If we remove the fluff, what are we left with?
N to the negative 1/2.
Yeah, we have root n over n, right? Which is 1 over n to the 1/2. So that's what we think of comparing it to, right? Okay, so then we go, all right, so we take the limit as n goes to infinity of root n over n minus 1 over 1 over n to the 1/2. So this is the limit as n goes to infinity of n over n minus 1, which is equal to
Yeah. 1.
1.
This is 1.
So what does that mean? Diverges, right? So since my original 1 over square root of n diverges, it's a divergent P and P series, right? Then the series root n over n minus 1 also diverges. By the limit comparison test, right? By the LCT. All right, so how many tests did we add to our toolbox today?